Good day and welcome to the first part of our discussion on optimization problems. Optimization problems are Chapter 3's version of related rates. They are always going to come in the form of some type of word problem. They require us to read through the problem thoroughly, kind of set up a calculus problem to solve, and then solve it. And similar to my warning for related rates problems in our previous discussions, these are problems that students typically find challenging, which is a fantastic indication that you need to set aside some extra time to practice additional optimization problems. But from a positive perspective, we will always have a nice procedure that we can use or thought process for approaching these problems. Now, in terms of motivation as to why we should be interested in optimization, I think that's the easy part. That was, in a sense, kind of the motivation for calculus in general. How can we maximize profit, minimize cost, minimize transport time, maximize efficiency? And the list goes on and on. So for now, when we encounter one of these optimization problems, how should we approach them procedurally? Now, the first step is hopefully not surprising. You need to make sure that you thoroughly read and understand the problem. And I know that sometimes sounds silly for me to say or for you to hear, but you really need to spend a moment, read the problem. Some things to focus on. What are the unknown quantities? What are the given quantities? And regardless of the problem, we want to draw some type of picture to help us out. And in that picture, we're going to have to introduce some notation. So we are going to label things with symbols for all of the unknown quantities. And then we are going to express the quantity that is going to be optimized in terms of the other symbols. And this is the key here. We need to express it as a function of just one variable, say f of x, on a specified interval. For each and every optimization problem, you need to write down for me a specific function, tell me if you're going to maximize or minimize it, and give me the interval of interest. That is to say, we're turning it into one of these extreme value theorem problems we've previously encountered. Once we have that problem identified, then comes the old part. Use calculus to find the absolute max or min on that interval of interest. And the best possible thing we can do at this point is just dive into an example and illustrate as specifically as possible how this procedure works. So let's find the area of the largest rectangle that can be inscribed in a semicircle of radius 5. So note a semicircle is a fancy way of just saying half a circle. And let's go ahead and draw a picture that represents this and see what we can do with the picture. So we have a semicircle of radius 5, so let's say the top half of such a circle, and we can very easily, and we will in a moment, write down an equation for this semicircle. But we want to find the area of the largest rectangle that can be inscribed in this semicircle. That is to say, a rectangle where the upper corners lie on the circle and the bottom corners are going to lie on the x-axis. So for all such rectangles, we would like to know what is the largest area. So when it comes to the area, it's determined by what? Length times width. So we need to somehow introduce some notation. I will choose, as we've done previously, to let x represent the distance that right lower corner of the rectangle is from the origin. And I will let y represent the height, which indicates that this upper right corner is on the semicircle at a point of the form x comma y. And the area of this rectangle can be written down very conveniently as length, so 2 times x, multiplied by height. And this is not what we want, at least not quite yet. we need to write down a function of one variable that we would like to maximize on some interval. And in order to turn this into a function of just one variable, we need to go back to this constraint we have, the rectangle being inscribed in this semicircle. So let me just kind of note in general as a reminder, as it's something we encounter, x squared plus y squared equals r squared would be the equation of a circle with center at the origin and radius given by r. So if we want the semicircle of radius 5, that would be the top half of the circle, whose equation is given by x squared plus y squared equals 5 squared. But note that describes the entire circle of radius 5, so the top and the bottom. If we solve for y, we could first isolate the y squared, and then note that y would be plus or minus the square root of 25 minus x squared. And if we specifically want the top half of the circle, it's really just the positive y we are interested in. And this quantity, the square root of 25 minus x squared, can be substituted in for y, which allows us to have an equation of one variable that we can maximize. So we have a of x now is 2x times the square root of 25 minus x squared. And what we would like to do is maximize this function on some interval. And what is the interval in which x lives in? X can be as small as 0 and as big as 5. And in this example in particular, you can see that this is where the picture really is handy to identify that interval in which x will lie on. And what I want to note is once we get it to this point, and this is something that you will always have to do, write a function of one variable, tell me if you want to maximize or minimize on some interval. Points will be awarded for this, so make sure you include this information. Once we have done so, note this is a familiar problem, a continuous function on a closed and bounded interval. So we need to do what? Find any critical points in between 0 and 5, evaluate the function at the critical points, and the endpoints of the interval. Once we have done that, we have a list of values, the largest of which will be the absolute maximum. So let's dig in. In terms of the calculus portion of this problem, we need to differentiate. And we will differentiate using the product rule. We take the derivative for the first times the second plus the first times the derivative of the second. And when we differentiate this second function, the square root of 25 minus x squared, we need to use the chain rule. So we think we take the derivative of the outside function, evaluate it at the inside function, multiplied by the derivative of the inside function. And note immediately we can get some simplifications. We have the 2's cancel. And I'm going to go ahead and leave out a couple of the algebra steps because we've done some very similar computations recently. If you combine this together in terms of a single denominator, the square root of 25 minus x squared, the associated numerator would be 50 minus 4x squared. And in order to identify the critical points, we set this quantity equal to 0 and we solve for x. Because it's a fraction, this is equal to 0 precisely when the numerator is equal to 0, which indicates what? 50 is equal to 4x squared. 50/4, or 12.5, is x squared. So plus or minus the square root of 12.5 is going to be equal to x. And these will be our critical points of interest in this problem. Now, note, are there any other critical points? And the answer is, yeah. If we look at our original function, its domain would be any input between minus 5 and positive 5. But if we look at our function a prime of x, it's undefined at plus or minus 5. So I'll go ahead and throw in here that plus or minus 5 are also critical points. It just turns out they do not have an effect on this problem because 5 is already the endpoint of our interval and minus 5 is not in it. So now that we've determined our critical points, we need to evaluate the function at a few locations. We need to know what is the value of the function at the endpoints of that interval, and what is the value of the function at any critical point in between. So if we substitute into our original function a of x 0 or 5, we automatically get back 0. If we substitute in the square root of 12.5, we would have 2 square roots of 12.5 times the square root of 25 minus the square root of 12.5 squared. And if you go ahead and simplify that, it ends up being 2 times 12.5, which is 25. And that value 25 is the biggest output we see on the list, and that gives us the absolute maximum value. And a very important part of all of these optimization problems is going to be a written conclusion. So the area of the largest inscribed rectangle is 25. And since we have been given no units associated with distance, it's perfectly fine in this case to not include units. But if units are ever included in the wording of the problem, you should certainly include those when possible. Now, the key ingredients that you must include. So there must always be a picture where you've introduced notation to represent those changing quantities. And then you need to somehow set up a function of one variable. Tell me if you're going to maximize or minimize on an interval. Points are awarded for having this statement. Now note, you don't usually just write it down. You first start off with something involving multiple variables or quantities, and then you use your constraining information, here the inscribed circle, to get it as a single variable. We then solve this problem using calculus, including all of our work, and we finish with a concluding statement. So tell the person reading your work what it is you have decided upon. For example, in this case, we were asked to find the area of the largest rectangle inscribed in this semicircle. So our conclusion, the area of the largest inscribed rectangle is 25. You could certainly make it a more elaborate statement, but that gets the information across in a very efficient way. So we will continue on exploring more examples in the upcoming videos, but this would also be a great opportunity for you to pause and go to some suggested problems and see if you can work through one or two examples. Stay tuned and take care.